I don't know why, but lately I just feel like talking in nature. 我不知道为什么，但最近我就感觉想在大自然讲座。So last time we talked about derivatives, the different types of derivatives, partial derivatives, gradient, Jacobian, Hessian. 所以上次我们讲了各种各样的导数，偏导，梯度，Jacobian, Hessian. And I gave you a problem to think about, which is, can we multiply and divide and invert partial differentials the same way that we can multiply and divide and invert differentials. 然后我上次最后给你们留了一个思考的题，就是我们能不能对待偏微分就如同我们对待微分，就是那个 partial x 和 partial y 能不能像 dx 和 dy 一样乘除还有叫什么逆过来倒过来Well, I didn't really tell you the answer. 我没有真正的跟你说答案 but now I will. 但现在我会。It's easiest to visualize a surface. All right. Z is a function of x and y. 最容易就是画图，比如一个面，曲面，z 是个函数，它的输入是 x 和 y。Then, df or dz is if you go from one point on the surface to any other point, but infinitely close. Then dz is the total change in z, or the change in height between these 2 points. 然后这个微分 dz 它的意思就是你从这个面上的一个点到面上的另一个点之间的 z 的差别是多少，就是那个高度变了多少，而且这两个点是无穷尽的，就是微微的距离。So it's a differential, infinitely small difference in distance between the 2 points. 然而偏微分就是 partial z。Well, 那得看你是偏微分对于哪个方向，就是你可以有偏微分就是 z 对于 x 的偏微分，或者 z 对于 y 的偏微分，那就是 partial z partial x 或者 partial z 除以 partial y。所以偏微分就是从这个点那个 partial z partial x 就是你往横的方向 x 方向挪到一个无穷尽的另一个点，那么 partial z partial x 就是这个 z 的变化除以这个 x 的变化，就是那个斜度。然后 partial z partial y 就是你要是往纵的方向，就是 y 的方向到无穷尽的一个点，这个 z 的区别除以 y 的区别，也就是 z 在 y 方向的斜度。Okay, now partial z, the meaning is, well, it's partial z, the partial derivative with respect to what? So you could have partial z partial x, so that's the partial derivative of z with respect to x, or you could have partial z partial y, which is the partial derivative of z with respect to y. And partial z partial x is if you take a point on the surface and then you move in the x direction to a point that's infinitely close, then partial z partial x is the change in z divided by the change in x. In other words, it's the slope in the x direction. And then partial z partial y similarly is if you start from a point on the surface and you move to an infinitely close point in the y direction, what is the change in z? And then divide it by what is the change in y. So it's the slope in the y direction. 所以你可以看出来dz 跟 partial z 的区别了。So now you can see the difference between dz and partial z. We can't even talk about partial z. We always have to say partial z with respect to what. 我们不能直接讲 partial z. 我们必须得说 partial z 具体是对于哪个方向的 partial z. Meanwhile, dz is just the change in z as you go infinitely close to another point anywhere in any direction. 然而 dz 就是任何 z 的变化，当你挪了无穷小的距离到另一个点，而且是往任何方向。So that's why dz, you can multiply it and divide it, right? You can do dz divided by dx. You could do dx divided by dz is equal to 1 over dz divided by dx. 所以这就是为什么你可以乘除 dz， 你可以做 dz 除以 dx， 你可以做 dx 除以 dz 等于1除以 dz 除以 dx. But the same is not true for partial z. If you did partial z partial x, that's the slope change of z as you change in x. 但我们不能对偏微分 就是 partial z 做同样的事情，因为你要是有 partial z partial x， 那就是z 对于 x 方向的斜度。But if you take partial x partial z, it's not gonna be 1 over partial z partial x. 但你要是做 partial x partial z， 那不等于1除以 partial z partial x, because you would have to rotate the graph so that x is here and y and z are the inputs. 因为你必须得转换这个图，使得 x 是那个这边，然后 z 和 y 是输入。然后你要是从一个点往 z 的方向走，然后你去计算 x 的变化，然后你做 partial x 除以 partial z， 这个跟 partial z partial x 不是正好倒过来的，或者逆的 inverse。So now, if you start from a point and go in the z direction, and then you find the partial x divided by partial z, or the change in x divided by change in z, which is partial x partial z. 所以这个其实是不是 partial x 除以 partial z， 是 x 的变化除以 z 的变化，然后它叫做 partial x 除以 partial z， 也就是写成 partial x partial z 的。Okay, so now you take the change in x and divide by the change in z to get partial x partial z, and that's not gonna be just 1 over partial z partial x. That's not just gonna be the inverse. You don't just flip the partial z partial x. Maybe we should draw an actual example, find an actual counterexample. 也许我们应该画一个具体的例子，就是找到一个具体的反例。Well, obviously it's going to have to be some wavy shape. It's not going to be flat, because then the derivative is 0 in all directions. And it's not just going to be sloping, so the derivative is constant. Maybe the derivative is like partial z partial x is let's say z is equal to e to the x times y or something. Then partial z partial x is y times e to the x. Or how about z is just equal to x plus y? Then partial z partial x is 1. No, how about no, that's too easy. How about z is equal to x times y? So partial z partial x is equal to y. So that means x is equal to z over y. Ah, dang it, partial x partial z is 1 over y. Gotta find a case where partial x partial z is not partial z partial x inverse. main thing is that x depends on both z and y. Z depends on both x and y. Maybe something more complicated, like z is equal to x plus y over x. Or z is equal to 1 plus x all over y. Then partial z partial x is 1 over y. X is equal to zy minus 1. Dang it, still doesn't work. Okay, maybe z is equal to x plus y over x. Partial z partial x is easy. It's 1 minus y over x squared. Which is x squared minus y all over y squared. And I'm pretty sure partial x partial z is not going to be x squared all over x squared minus y. Z is equal to x plus y over x, or x squared plus y all over x. Aha! Now we can't get x is equal to just some straight function of y and z. We have to do implicit function and implicit differentiation. So z is equal to x squared plus y all over x. Z times x equals x squared plus y. Oh, we could still solve this for x. X squared minus xz equals negative y. Oh no, we can't. Okay, x squared minus xz plus y equals 0. Now using chain rule, 2x, so take the derivative of f of x with respect to z. So 2x partial z yeah, basically if you ever get an implicit function, then you can take the derivative of both sides with respect to z. But both the x and the y depend on z. So you're going to get some partial x, partial y, times partial y, partial z, plus partial x, partial z. Is equal to dx dz. And then I'm pretty sure that you're not going to get things working out right away. Yeah, like the inverse. Okay, 所以只要是你有隐函数，还有隐的，就是要用链式定理求导，那时候你就不得到那个 partial z partial x 等于1除以 partial x partial z， 因为比如你可以说z 等于 x 加 y 除以 x， 那就是 x 平方加 y 全部除以 x， 然后 partial z partial x 这时候等于1加负 y 除以 x 平方，但 partial x partial z 应该不是1除以这个了，因为你根本不能说 x 等于一个函数，而且这个函数的输入只有 z 和 y， 你必须得得到就是什么x 平方加 y 全部除以 x 等于 z， 所以 x 平方加 y 等于 x 乘 z， 所以你没法说 x 等于一些 z 和 y 的函数，你只能最接近就是 x 乘上括号 x 除以 z b 括号等于负 y。然后这就是最接近 x 等于某个函数了。然后你要是这时候想求 partial x partial z 的话，那你可以两边都求对于 z 的导数。但因为 x 和 y 它们两个都依赖于 z， 所以你必须得求 x 对于 y 的偏导，再乘上 y 对于 z 的偏导，再加上 x 对于 z 的偏导，才能得到 x 对于 z 的导。And that is the key, is that if you want to find dx dz now, that's d, all right, not partial x partial z, it's dx dz. Now you have to take partial x partial y times partial y partial z plus partial x partial z. 所以那就是关键，就是你现在要是想求 dx dz， 那就是导数而不是偏导，那你必须得做偏导 x， 就是 x 叫什么 partial x partial y 乘上 partial y partial z， 再加上 partial x partial z 了。Yeah, so you could just do this. You could just take, so now we can just, make our example simple, is that, well, let's just take any dz dx, all right? Or, any partial z, partial x. Well, okay, we know dz dx is 1 over dx dz. Okay, 所以现在我们可以就是做非常简单的叫什么广阔的例子了，就是纯证明 just directly prove 我们知道 dz dx 等于1除以 dx dz. And now we can just directly prove that well, partial z partial x and partial x partial z, where do they fit in here? 然后我们可以直接证明那 partial z partial x 和 partial x partial z 它们在这里处于哪儿呢？ Well, we have dx dz, or dz dx is equal to partial z partial y times partial y partial x plus partial z partial x. And dx dz is partial x partial y times partial y partial z plus partial x partial z. And those two are clearly not just one divided by each other. Done. OK, 然后它们处于哪儿呢 ？Well, dz dx 等于partial z partial y 乘上 partial y partial x 再加上 partial z partial x。dx dz 呢等于 partial x partial y 乘上 partial y partial z 再加上 partial x partial z。然后这两个明显不是就是互相的逆或者互相的一除以另一个，或者倒过来。So they're not just take one, flip it over, and you get the other. Yay, that answers last time's question. Yay, 这就回答了上次的问题。But now I have a pop quiz. Because we have learned some things about limits. And we have learned some things about microcosms and macrocosms, and I'm sure that you have seen fractals. OK, 但现在我们有一个惊喜的另一个测验，因为我们之前学过一些关于极限的知识，然后我们也学过一些关于大周天、小周天，然后我估计你以前见过分形。So just for fun, take the simplest fractal, which is a Fibonacci spiral. I would recommend making a Fibonacci spiral out of golden triangles. So that's isosceles triangles whose side lengths are in the ratio of 1 to the golden ratio, 1 plus root 5 all over 2. And then draw this. Okay, so you got first triangle. And then the second triangle takes the long side of the previous triangle as its short side, and then goes in the direction of the short side of the previous triangle to make a long side, and then it's an isosceles triangle, so you get the other long side, and then you get the next triangle. And then you keep doing this. So you take the next long side going in the same counterclockwise direction and make that the short side of the next triangle. And then you go along the previous short side to make a long side. And then you go symmetrically to make an isosceles triangle to make the third or the other long side. And you just keep going, all right? And then it'll, if you connect the corresponding vertex of each, then you'll get a spiraling out. But you could also go infinitely inward, spiraling in. All right, so now can you find the center of the spiral? Now the Fibonacci spiral, it will keep going inward forever, all right, without ever hitting itself or stopping. So it will never actually reach the center. So that's why the center is a limit, because it just keeps approaching it forever without actually necessarily reaching it. So yeah, can you find the center of the Fibonacci spiral? It's going to be a limit. And then why is it fractal? Well, duh, it's self-similar. But you could also try to apply the formal definition of a fractal in terms of like having structure at all levels. Well, okay, that's kind of the same thing, but also in terms of Hausdorff dimension. So you could also try to challenge yourself and be like, well, what's the dimension of a Fibonacci spiral? And is it kind of like, finding the dimension of the Cantor set or the Koch snowflake or the Koch snowflake, however you pronounce it? You could even explore and be like, how would you draw a Fibonacci spiral using a computer, like an accurate Fibonacci spiral? So it's like not just, some of the points and then you connect the in between, but like how would you draw every point? There's just like so many things you could explore with fractals. So just, do whatever you feel like, whatever interests you. OK， 所以现在我们的惊喜测验题目就是你就拿最简单的分型，那就是 Fibonacci，叫什么？就是从里到外一直循环，但越来越大，也可以从外到里往里循环。Spiral，OK， 哇，然后我建议你用那个金子数字 golden ratio， 金子比例，金色比例 ，yeah golden ratio， 的金色三角形做的 Fibonacci 循环。那是怎么做的呢？就是你画一个三角形，它是有两个长的边是对称的而相等长度的，然后它的底基那个边，然后这个边和这个边的比例是1对于金色比例，就是1加根号5全部除以2，所以这个是1，这个是1加根号5全部除以2。然后你再拿之前的三角形的长边当做下一个三角形的短边，然后你沿着之前三角形的短边产生一个长边，然后你再用对称，因为这个三角形是两边相等的，congruent， 两边一样的 ，OK， 所以另一个长边你就能够画出来了，然后你就能够画出整个第二个三角形，然后你再这样继续，就是下一个三角形你就拿之前的三角形的长边，而且继续往这个逆时针方向当做它的底基或者它的短边，然后你再用之前三角形的短边，沿着这个短边画一个长边，然后你再用对称性画另一个长边，然后再继续，然后它们会旋转，而且变得更大，而且你要是把每一个相似的点连起来，你就得到一个 Fibonacci 循环，而且这个是自相似的，就是它能够一直往外无穷多，然后也可以一直往里无穷多次，从来不会碰到自己，从来不会结束。然后你可不可以用你知道的关于极限的知识，计算它的中心在哪儿？那就是一个极限，因为它一直都在趋于那儿，但永远不一定达到，它就永远离得越来越近，越来越近，但不一定达到。 所以你能不能求它的极限在哪儿？其实你也可以做其他东西，就是这显然就证明这个是自相似的，然后就是要是用大概的分型定义，它就是自相似的，你就知道，哎，这个斐波那契环是个分型，但循环，但呢，你也可以用更正式的定义看一看，判断这个斐波那契循环是不是一个分型。比如，当然有一个稍微正式一点，但也不还算是一样的，差不多一样的意思，就是它不管你拉近多少，往外拉多少，它总是有结构的，但非常正式的定义就是关于 Hausdorff 维度，你可以试一试计算斐波那契循环的 Hausdorff 维度，然后你可以对比一下，就是它的计算跟那个 Cantor 集合的 Hausdorff 维度，有什么类似吧？或者 Cock Snowflake，有可能是应该是念成 Coke Snowflake， 我忘记了，就是那个另一个分型，那个雪花分型。你也可以做更多，就是你可以就是探索无穷多关于分型，就是你可以看，哎，能不能画这个分型，就是不只是画这么一系列点，而是中间的点也都能够画的，而且画的准确。比如用一个计算机画图。或者不用计算机也行，但能不能找到一个方法，能够不只是画几个点，然后你自己就是把之间连起来，而是你能够画每一个点。反正哎，你想做多少就做多少，就是可以探索，看你做多少。Okay. Oh yeah, back to. I just wanted to conclude with, everything is under the illusion of separation. According to the law of one, in our three-dimensional world, we have a veil of separation. It's as if we are all one flame, one soul. But instead of seeing the flame or the soul, we only see the various windows of the soul. We see the soul through various people, through various windows to the soul. 然后回到一元法则，我就想说一个，就是一切都是一个分开的幻想，就是其实我们都是同一个火，同一个灵，但在我们这个三维世界，我们看不到那个火，那个灵，我们只能看到它从不同的窗户 的不同观点，就是他从不同的人表现出的这个零，同一个零，不同的窗户。这就能够解释很多很多世界的现象。This can explain so many things. 比如，很多你们年轻人，比如我当时，读大学、读博士的时候，我们都在找对象。或者恋爱关系什么的，找来找去，最终其实都是一体的一部分，一个零的一部分，一个火的一部分，搭上一体，一个火，一个零的另一部分，然后也许后来一体的这部分跟一体的另一个部分跑了，然后跟一体的那个部分分手了，唉。但最终，我们真正求的是那个来源，是那个火本身，那个灵本身。那不是外求的，那是内求的，然后包含一切根源。然后我有个猜测，就是现在我们比较更成年一点的人都在找工作，或者在工作，或者在换工作，其实都是类似的，可能是完全同一个回事，然后就是同一个结论，就是一切都在缘，缘就是一切。你有了缘，你就什么其他的都不需要。但你什么都有，没有缘，你是什么都没有的。然而，那些整天骚扰我的，其实他们真正就是他们可能说的是他们要对象，或者他们要钱，或者他们要性交或者什么，但其实他们真正的意思是他们在求光，那个纯光、纯火、纯一体、纯灵。所以